हाँ, जस्ट बिकॉज थिंग्स आर गेटिंग रिकॉर्डेड, तो इससे बढ़िया मैं दीवार से बात करके उसको रिकॉर्ड करके फिर तो लाइव आने का किसी को ज़रूरत नहीं है। आई थिंक दैट इज़ पॉइंट नंबर 1। पॉइंट नंबर 2, डिड यू सी द लास्ट सेमेस्टर वीडियोज़?
यस सर।
उसमें मिला तुमको?
यस सर, उसमें
हाँ
इलास्टिक प्लास्टिक का मिला है सर।
हाँ, तो इट इज़ द सेम विच वी आर डूइंग।
यस सर।
ज्योमेट्री सेम है, अप्रोच सेम है, सॉफ्टवेयर सेम है, प्रोसेस सेम है।
यस सर।
ठीक है,
यस सर।
तो फिर क्या प्रॉब्लम है?
सर प्रॉब्लम नहीं, मैंने नहीं वो लिखा था
अच्छा,
सर।
so you are saying lecture में missing है, that is
Yes,
good,
yes.
that is good. So now
Nothing
from
else
now
from my
on
part, sir.
onwards I'm recording using a software. I hope that will work. हाँ, बैकअप के लिए जो है वो गूगल मीट भी चला सकते हैं, टू मच फाइल्स हो जाएगा। आई थिंक इट शुड बी ओके नो टू रिकॉर्ड इट फ्रॉम, साउंड इज ऑल्सो कमिंग, सो इट्स ओके। लेट अस सी जो भी इस लैब में हो रहा है वो पहले हो चुका है, ठीक है। सो आई एम नॉट चेंजिंग लॉट ऑफ डिटेल्स टुडे, आई विल चेंज लिटिल बिट, पर वो एड ऑन ही होगा, इट विल नॉट बी कि वो डिफ़र कर जाएगा, ठीक है। अच्छा, ये अवनीश, आर यू देयर?
यस सर। यस सर।
संतोष को ऐड करो क्लास में, उसको लिंक भेज दो।
ओके सर, ओके ओके।
I will have to add him, it will take some time, so you please add
नो
him.
सर, आई जस्ट सेंड। ओके, नो प्रॉब्लम।
Just share the link with him. Acha,
Okay.
fine. So, see, initially what we did, and right now I'm not sharing anything. In a minute I will share whiteboard. So, so I have explained the theory in the beginning, in the first lecture. ठीक है, and today I will elaborate a little more with the theory part, and I will try to make it as easy as possible, but ये जो है वो थोड़ा सा तो difficult है in comparison to other courses जिसमें मैथमेटिक्स का कोई लेना देना नहीं है ज़्यादा, उससे थोड़ा difficult तो आपको लगेगा ये कोर्स। और दूसरा प्रॉब्लम क्या है कि दिस MM308 एंड MM311 दे रन टुगेदर इन one semester, so and usually is shared by me and Dr. Prince. So क्या होता है कि if somebody is taking the theory first, तो उसको added advantage मिलता है कि theory will be explained before the lab starts, but the one who starts the lab first has a disadvantage that theory जो है वो बाद में explain करना पड़ता है। and so one solution could be कि दोनों साथ में किया जाए, and second is which I am going to try is that I will take one class which is today and I will try to explain not in much detail but in little bit what we are doing, right? And hopefully that will help in understanding what happens behind the software. Software is just an interface, and whatever happens that we will try to understand today. Okay, just a second. So has Santosh joined? So far no.
यस सर। डॉक्टर
Oh,
यस सर।
okay, you have joined. Okay, fine. So I have not responded to your email, but you can sit through this course. Okay.
ओके।
So, but what you have to do is that you have to watch the previous lectures, previous labs, and you join the classroom also. Please share the classroom link with him, and there you will see the playlist which was done for the previous semester. So it will help. We will have to dedicate some time, even though you are sitting through. Okay.
Yes, sir.
You'll have to give some time. You have to spend a lot of time on the software, because until you do it, you will not be able to, learn this thing.
Yes, sir.
All right. Okay. So if you remember, and I hope everyone is looking at the whiteboard, we solved this cantilever thing, right? And I'm set with this automatic thing. Okay. So what we did there was that we divided, so we assumed this to be, so we simplified this and we assumed that this line represents this cantilever, which has an area which is changing gradually with the in the x direction. Okay, so here at point A, I cannot write A, at point alpha area was 7a, and at point beta the area was a, right? So you have 2 points, so you could formulate what will be the expression of area. And then basically what we did is that we divided this cantilever into n number of elements, right? So this is element number 1, this is element number 2, element number 3, element number 4, and so on. You can divide it into as many number of elements as possible, and what happens is that if you divide it into many small pieces, then as small the elements will be, that closer you will be to the real result, to the analytical results, right? But you can never approach the analytical solution, because for that you will have to create infinite number of elements. So this is called discretization. So you divide the object into smaller pieces, and then what you do is you solve everything in that small piece, right, in one element, and then you add on, at the end you add on all the contribution of all the element, and that's how you solve the total problem, by dividing into smaller and simpler problems. So the essence of finite element analysis is that a curve is a straight line if you divide it into smaller pieces. So it is just a straight line which is changing angles. So solving a equation of a circle may not be easier in comparison to solving the equation of a line, right? And that is the idea, to make it simpler. Now after making it simpler, you can introduce a lot of complicacy. So you can take a smaller element and say that instead of taking a line, I'll take a parabola there, and that parabola will be changing direction. Okay, so you can do all those complicacy. And usually what happens is that if you divide something, any object, into n number of pieces, so n number of elements, then as I said, if you increase the number of elements, you increase the accuracy. But the problem is that when you increase the number of elements, it becomes computationally cumbersome. So it is heavy on the computation, right? And computational cost is too much. So cost not necessarily means money, but also time, and you will have to have great resources of computers and all, with good memory, good solving speed and other things. So that becomes costly. So this is called this is one type of approach which you can deploy to get accuracy. Another kind of approach is that you don't divide it really into very small pieces, but you divide it into comparatively coarser elements, and then you use, instead of linear interpolation, you use higher order interpolation. So you use a higher order degree of interpolation, which we call shape function. Okay, is this so far, is this clear to everyone?
Yes, sir. Yes, sir.
Okay, now let us say that we are going to define a degree of freedom. So degree of freedom is what we call something which is being interpolated at different discretized elements. Okay, so let us say that I have an object which looks very simple, which is a square. Okay, and then I divide it into smaller pieces. And I have a problem. The problem is that this box is constrained on the lower side, so it cannot move in, let's say, x direction, and it also cannot move in y direction. Only this part, only the lower edge. So it's like you have a block which is welded on the ground. Okay, this will not stop. Okay, there is no click. Okay, I will not do that anymore. So this is the part which is welded, right? The lower edge is constrained in this way. And let us say that we are defining that we are applying some displacement on the upper edge. Okay, so uy is equal to some value, 2 millimeter or something, but ux is also 0 there. Okay, and this is the problem which we want to solve. You can solve it analytically, just a block which has ux is equal to 0, uy is equal to 0 on this edge, and here you have uy is equal to 2, ux is equal to 0, right? So you can simply solve it. If it is linear elastic, then you know that how much displacement is going to be based on this kind of relationship, right? So where k will be elastic modulus into strain, and then if you know the dimension, you can solve it, right? So that is pretty simple. But when you divide it into smaller pieces, then what FEM is doing is that it is taking and solving each element. So let us take this element out, and it is going to solve this, the degrees of freedom in this element. And what is the degree of freedom in our continuum mechanics problem? So this is called continuum mechanics because the material is in continuum, right? So there is no discontinuity. So we cannot incorporate any hole damage. I mean, hole we can, but we cannot incorporate physical metallurgical things like inclusion and carbides and damage as it is, like literally damage, like voids and all, we cannot incorporate. We cannot incorporate dislocations and all those kind of things because those are discontinuities, right? So we imagine the material to be continuous. It can be heterogeneous, but it is continuous. Okay, so there is no discontinuity between material, there is no gap. Okay, is this understood? So as long as I define an object, it can be a complicated object, it can be a gear, it can be anything, but wherever the material is, that material is continuous. Okay, so we are in that continuum zone, and there we have, what degree of freedom are we solving here in this case? The degree of freedom is the parameter which is being discretized and being solved in each element, and that in this case is displacement. Okay, so displacement is the degree of freedom, and we will see. So in two-dimensional problem, you have on this element you have 4 nodes. Okay, so the 4 corners are 4 nodes, and so let us say this is node number 1, node number 2, node number 3, node number 4. And on node number 1 you have displacement, and what how many types of displacements can you have there? You can have u1. So 1 denotes the direction and the superscript denotes the node number. So you will have u11 and you will have u12, right? Apart from that, will you have any other kind of displacement on node number 1?
No, sir, I don't think.
Okay. Right. What about rotation?
Means net if upward direction and rightward direction, then there will be a vector as well. So will that be possible?
Say it again.
If A1 dash is upwards and if they are means like forming a right angle type thing and there will be a vector between them, so will that be possible in this case?
I still don't understand. But if you are saying this, so we have this coordinate system is x and y, which sometimes is denoted as 1 and 2. Okay.
Yes, so between 1 and x and y there will be a line passing through origin, that way vector type thing. Will that be possible, sir?
Okay, so let me explain this. So this is the object, one element I have taken out, right? And this whole element, in reality what this is that this whole element is a continuous sheet of material, let us say, right? And so displacement is going to be everywhere, right? But because of our discretization, we are only calculating displacements at these 4 points and there is nothing in between, right?
Okay.
And we can refine it, so we can also divide this into a number of pieces, right? So there you will have to create more elements here, and you can, so basically what is happening is that this object in reality is defined by infinite number of points, right? But when you divide it into finite number of pieces, then you are defining it by finite number of points, right? So only those finite number of points are contributing to your calculation, and by solving them you will get the value, but those values are coming from the finite number of points, right? And this displacement is a vector, it is a vector, so that's why you have a component in x direction and a component in y direction, right? So the degree of freedom which is there is displacement vector, which has u11, that is in x1 direction, so ux and uy. Apart from that, you don't have rotation here. We don't have rotation. Why we do not have rotation? Kanupriya?
Because stress is only present in one direction.
What is present in one direction?
Stress. We are displacing it only in one direction.
So if I apply a displacement like this, then will there be rotation?
No, shearing will be there.
So when there will be
No,
rotation?
not shearing.
So there will there be any case where there will be rotation?
So because there is no torque.
No. So okay. Do you remember the displacement tensor we talked about, and we took out strain tensor and rotation tensor out of that? You don't remember? Symmetric and skew symmetric tensors.
Sir. Yes, sir.
Last semester.
Yes, sir.
Yes, sir.
Yeah, so you have strain, which is this, and then you have rotation tensor, right? So this is strain and this is rotation, and this whole thing defines the total deformation, right?
Yes, sir.
So you don't have to really denote another parameter for rotation, because rotation can be calculated by the displacement field itself, right? So if there is any rotation, that rotation can also be calculated, so you don't really need rotation there as a separate entity. Why I am asking this? First, because you don't know or you have forgotten, and secondly because in so this is a homogeneous solid continuum modeling which we are doing, and you might have seen in the software sometimes it asks for shells, right? And when you take it as a shell, then we have plates theory and cells theory, where you do have a degree of freedom for rotation. Okay, but we will not go there. So that's a different, altogether a different game. Okay, so here we don't need to count separately for the rotation, because rotation is already calculated by the displacement field. So we really have to only calculate displacement. We only have two component of displacement, because it is a two-dimensional problem. If it is a three-dimensional problem, you will also have u3 at each node. So in one element you will have how many degrees of freedom? So you will have 2, 2, 2 and 2. Okay, so total you will have 8 displacement values, which are called nodal displacement values. Is this okay?
Yes, sir.
Okay. Now let me tell you something which is called isoparametric. So what happens is that we are discretizing displacement, and we are also discretizing something else, not necessarily, but it is happening because of dividing something into finite pieces, and that is the coordinate. Okay, so displacement field or displacement vector can be given as some coefficient into the nodal value of displacement, which let me write it as d. What does this mean? This means that if it is a finite one-dimensional problem and I have displacement, so because it is one dimension, I will have only displacement in the x direction, y direction I am not considering. So I will have, let us say, at node number 1, node number 2, node number 3, node number 4 and so on, I have displacement values as d1, d2, d3, d4, d5, right? And the total displacement at any point I should be able to write by a function which relates. So let us say I want to have the displacement value here at point A, okay, or at point B. So how can I calculate that? So that I can calculate by operating with this matrix on the displacement value. So it really will look like U is equal to N will be a matrix and D will be a column vector, which will be having d1, d2, d3 and so on values, which are called nodal values. Okay, and when the same matrix, which is this one, can be used to also describe the coordinates. So coordinate of point A can also be given by the same matrix operation on the nodal coordinate values. Then if this is followed, these two equations are followed for any type of element, then those are called isoparametric element. Okay, is this clear?
Yes, sir.
Okay.
Yes, sir.
Okay, good. So keep on absorbing, and now let us look at what happens when we take one element out. So this is one quadratic element which we are considering right now, and what happens is that, so let me explain a little bit on the one dimensional problem. So let us say there is one dimensional element E1, okay, and here you have a displacement value d1 and you have a displacement value d2, right? And now you have to describe the displacement throughout from node number 1 to node number 2. So for that you need a function which can tell you that how this distribution will be, right? And for that we take a function which has a value 1 here and 0 there. So how that function moves? It moves like this. So it will always have a value here 1, and at node number 2 it will always have a value of 0. Okay, and similarly, Charvak, you want to say something?
No, sir. No.
Okay, and similarly I will have same function defined at different nodes. So this function at node number 2 when I define, so it will have a value of 1 at node number 2, right? And at every other node it will have a value of 0, so that will also move like this. Okay, so imagine this to be, so it is a linear function, you don't have to imagine, which has a value of 1 here and 0 there. And what basically it means is that I am actually defining a local coordinate system for each element. Okay, so now let me explain a little bit on this. So this is my object, right? And this object will have some coordinate value. So let us say this is origin and the dimension of this object is 5 millimeter. Okay, 5 cross 5. So you will have different coordinate values, right? So here what will be the coordinate of this point? This point will be 0 on x axis, sorry, 5 on x axis and 0 on y axis, right? And this point will have x axis 0, y axis 5, right? And each point, each of these points will have different coordinate values, right? And it is hard to remember computationally. So if let us say I take this element out, element number 11, if I take this out, I will have to also take the information of what is the coordinate system there, right? And for each coordinate system I will have to do all those calculations, so that will keep on changing. So for each element you will have to write a different matrix, right? So as many number of elements you will have those many number of equations to solve. That is anyways true, but you will have different coordinates for each element, right? That is one issue. And then the other issue is, what if this box is not rectangular? What if I discretize this object in irregular mesh? So something like that. What if I do that? So then what happens is that it is going to be further complicated, right? I can do that also. This is also a kind of discretization. This is also a kind of meshing which I can have. I can have even further complicated meshing. I can have triangular elements included within rectangular elements. So I can have a combination of triangular and rectangular elements. Okay. So in that case, keeping up with the global coordinate is going to be a problem. So what could be the better way of dealing with this and becoming computationally cheap? Can you think of something? You already have a clue. Is anyone there? Kanupriya? Kanupriya? Avnish?
Yes, sir.
Attendance?
Yeah. Bobby? Can sir, ma?
Yes, sir.
Asima? Ankit? Yes, sir. Gokul? Harshvardhan?
Yes, sir.
Arjot?
Yes, sir.
Anupriya?
Yes, sir.
Shivaji?
Yes, sir.
Naveen?
Yes, sir.
Naveen? Prem Dayal?
Yes, sir.
Yes, sir. Rishabh?
Yes, sir.
Sanchit?
Yes, sir.
Anand?
Yes, sir. Yes, sir. Hello.
Satya Prakash?
Hello.
Yeah.
Yeah. Shyam Sundar?
Present, sir.
Yatin?
Present, sir.
Sachit, I think this is your first class, no?
Sir, you forgot others.
Sir, Vedant also.
Yeah, okay.
आदर्श वेदांत का नाम ऐड कर लो.
4 marks, sir, as well.
क्या again sir?
नहीं, so some of the students are missing in each attendance, so it looks like सारे का नाम है या नहीं है?
Sir, नाम है सचित आनंद continuously इनका first class है. I think this is a first class.
Yeah, that is okay, but you have others, Charvak and all those people, no, in the list?
Yeah.
ठीक
Yeah.
ठीक, okay, fine. Okay, so the better way to deal with all this is to define a local coordinate system, and that local coordinate system for a quadratic element is something like this. So I have in this box, which is one element of the whole thing, I have a local coordinate system, and in that case local coordinate system is also Cartesian coordinate type, but we will not denote this with x and y or 1 or 2. This has a special symbol, so this is zeta, looks like epsilon, and this is eta. And the rules of local coordinate system is simply that on this end it has a value of -1, and on this hand it has a value of 1, and eta also -1 and 1. Okay, now it looks good when you have this regular square shaped body, but it is also true if you have an element like this. Even in that case, the local coordinate system will always define this by -1 1 and -1 1. Okay, do you understand? So whatever is the shape, the local coordinate system is also always going to change it to a square of the dimension -1 to 1. So the coordinate system is not going to change for any element locally, and all that calculation will happen locally with this coordinate system, and at the end you will have to convert it to the global coordinate system, which you will have to do, but only once. Okay, do you see the advantage here? The advantage is, yeah,
I have a doubt.
yeah,
Sir, if we reduce that to a square, then the shape will be changed according to the coordinate system which we used.
yes, yeah, so that's what, so it will always change it to a square in local coordinate system. Okay, but
Yes.
when you convert it back to the global coordinate system, the shape will convert back to that. How is that going to happen? It is going to happen by the relationship between local and global coordinate system.
Yes.
Okay, so that is how it is going to happen. The advantage of this is that if you have 20,000 element in the model which you are making, instead of doing the calculation for different value of coordinates for 20,000 element, you are doing the same calculation, similar algorithm for 20,000 element, and one computation at the end where you convert the local to global coordinate system. Okay,
Yes, sir.
so that's the advantage of this, and this is what happens. So locally this has happened, and I will not tell you the details of this here right now. We will deal with this because this involves a lot of calculation, this matrix. So right now you just focus on this, that this is a matrix which defines the relationship of a variable which is continuous with the discrete value of the same variable at the nodes. Okay, so the displacement value at each node is d1, d2, d3 and so on, and if you want to find out the displacement at point A or point B, you will have to do this operation. Okay, and this matrix is called the shape function. Okay, and this is the same thing which I was describing here. So shape function has a property, and that property is the following. The property is that the shape function will always have a value of 1 at the node where that shape function is defined. So the node number 1, in this case the shape function will be, if it is a one dimensional problem, so that is 1 minus zeta by 2, and at node number 2 the function will be 1 plus zeta by 2. Okay, I will not derive this right now, but these are the values of the shape function, and you can check at any point. If so, the value of zeta is here is -1, and here it is 1. So if you put those values, you will get the value. So let us put the value of zeta at node number 1 it is minus 1, right? So 1 minus minus 1 is 2, by 2 is 1, right? And if you calculate at node number 2 where the value of zeta is 1, so it becomes 0, right? So the value of n1 at node number 2 is 0, and this is going to be true for further elements also. Node number 3 also it will be 0. So at any node except the node where the shape function is defined, the value is going to be 0, right? Is this understood? But what is the value here? It's here it is not 0, and that you can see from this line, and you can also guess what is the value here.
Yes, sir, 1 by 2.
Yes, right? And this is going to, this defines the relationship between the nodal values and the variable of the displacement. So the varying value of displacement, the continuous value of displacement. Okay, so if I have to calculate u at the middle point, then u is going to be n1 u1 plus n2 u2, okay, or d1 d2, because u2 you might get confused with uy, so d1 d2, right? So the d1 here in this case, because it is fixed to the wall, d1 is going to be 0, d2 let us say is 2, right? And so node number 1 value at that midpoint is half, so half into d1 is going to be 0 plus half into d2 is 2, so the value of displacement at the middle point is going to be 1 millimeter. Okay, so this is what defines the relationship of displacement, the nodal value of displacement and the varying value of displacement. Okay, so this, if this is clear, then we can proceed with this information that we can define the displacement with this equation. Okay, and now from this we have to find out what is the value of strain in each element, and we are doing it for each element. We are not doing it for the whole thing right now. We are dealing with one element at a time. Okay, so if you remember the strain matrix, we can define that as del u by del x, which is epsilon xx, then del v by del y, which is epsilon y by, and then we have del u by del y plus del v by del x, which is epsilon xy, and this is only, we have 3 terms because I am considering 2-dimensional problem, otherwise I will have 3 cross 3 matrix. Okay, so this is how I am going to calculate strain, right, analytically. And in order to do that, what you will have to do is you will have to partially derivate this displacement. You see that, right? So let us say if you have to find out epsilon xx, then you will have to find out this, and in order to find out del u by del x, what you will have to do is you will have to partially derivate n dot d, right?
Yes, sir.
Okay, so now what you have to do is you have to do the partial derivation of the shape function, right? And this here we have written here in this way, right? If you have in the quadratic element, you have 4 values of displacement in x direction and 4 value of displacement values in y direction, right? So in that case, how it will look like? It will look something like this. So n1 n1 n2 n2 n3 n3, because you will have 4 points, no, in a quadratic. So you will have something like this: 0 0 0 0 0 0 0 0, and then you will have a column vector which will be the local value of displacement. So here I will write u1 v1 u2 v2 u3 v3 u4 v4.
So
And
how did you
yeah.
write that first matrix? I didn't understand.
Which matrix? This one.
So this n
I'm going to tell you how. So because in each quadrilateral you have here u1 v1, right? You have u2 v2, u3 v3, u4 v4, right? This is okay, no?
Yes, sir.
Okay, so that becomes this column vector, this one, and because we have defined this, this is how you are going to get that formula, because n1 is going to, so first what will be the value of multiplication of these two? So this is how many columns? So you have 1 2 3 4 5 6 7 8, 8 cross 2, right? And this is 8 cross 1 cross 8, right? So this is okay. No, this is not okay. Oh, so we write rows versus columns. So 2 cross 8, 8 cross 1. So the result is going to be 2, right? 2 cross 1, right? So what will you get? You will actually get ux and uy, right? So when you calculate ux, what you do is you multiply this with this, okay? You multiply this row with this column, right?
Yes, sir.
So what will happen? You will see that all the y values will be 0 because you are finding out ux, right? So it will simply be n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, and similarly v or simply uy. So I will write sometimes, you know, there will be some mixing. So u, if I write u and v, so u simply means ux and v means uy. So this will be n1 uy1. Instead of writing that, I will write v1, n2 v2, n3 v3, n4 v4. Okay. So now this is my shape function matrix n, and I have to find out the partial derivative of that, and that is gonna look even a little bit weird, okay, because you are finding strain matrix. So this is going to look like something like this. So this is going to look like del n by del x and 0 0 del n by del y, and this will be n1 n1, and then you will have del n1 by del x plus del n1 by del y. No, not plus. So here it's going to be just like that, and this is for node number 1. Okay, so you have 4 nodes, so you will have 4 of these. So you will have del n2 by del x 0 0, del n2 by del y, and similarly here you will have 2 terms and so on. Why it looks so it is actually not complicated. So instead of writing like this in the matrix, you simply can write ui is equal to ni. So ux is equal to ni ui and uy is equal to ni vi. If you write it in this form, then it makes sense, right? Instead of this matrix term. So similarly, it looks like this because you have a strain matrix which looks like this. Okay. So in order to get del u by del x, you will always have del n1 by del x into u1. Okay. So this will convert. So at the end you will have again u1 v1 u2 v2 and so on. So when you multiply this row with that column, what do you get? You get del n1 by del x u1 plus del n2 by del x u2 and so on, and this defines your epsilon xx. Okay, and when you have to calculate shear stress, you will have to operate on both u1 and v1, right? So that's why you will have 2 terms. I think I made a mistake here. So this will be y, this will be x. Okay, is this clear?
Yes, sir. Sir, just go
Yeah.
little slow. It's
Okay. Fine. So it is so this is why we cannot explain this whole thing in the lab class, because I want to introduce what happens and how do we model rather than what happens in the background, which we are going to deal with in the theory. But because I got that comment that the theory part is not clear, so I thought maybe I'll tell you what happens in 2 dimension. In 1 dimension it looks pretty simple. Okay, in 2 dimension it is a little difficult. So let me reiterate what I said so far. So initially what I said is that there are elements where we are going isoparametric. So the coordinate values and the variable which is being discretized can be defined by the same function, which is shape function n. Okay, I hope this was clear. And
Sir.
yeah.
Yes, sir. Yes, sir.
Okay, so this is the shape function which defines the relationship between the nodal values of the parameter and the varying value of the parameter, and it also defines the relationship between the coordinate at any point with the coordinates of the nodes. Okay, coordinates of the nodes. So remember, it is not the local coordinate system, it is nodal coordinate system. This is nodal coordinate system. Local will come into picture only when we are dealing with one element at a time. Okay, so this is what isoparametric means, and usually in our whole course and even beyond, as long as you work in continuum mechanics and don't go into very complicated problems, you will always deal with isoparametric elements only. Okay, so this is what we said, and then in reality, in the calculation, the process is that in each element the displacement is defined using this formula, and from that the strains are being calculated. Okay, because you will have to calculate strain, then you will have to calculate stress. Okay, and then what? The real question is that how do you know that you have solved the problem? What is the governing equation? Okay, so for example, in thermodynamics, how do you say that a reaction is going forward, backward, or is in equilibrium? What is the parameter which tells you that this is going to happen?
The Gibbs
Right. So if del G is less than 0, that means it is going forward, and vice versa, and if it is equal to 0, then the things are in equilibrium, right? And similarly, we also have a concept here. So what happens? First, what we have to do is from displacement, and you must also know that at each nodal point we really don't know the values of displacement always. Okay, so sometimes the value of displacement is given before the problem, and sometimes the value of displacement is not known there. Okay, so you put it as a variable and you solve it. So at the end you will have an equation where you will have n number of unknowns and n number of equation, and you will have all the values at the end, right? So it's not that the displacement vector is going to be filled with known values always. That is not going to be the case. Okay, right? So displacement we have, from that we calculate strain, right? And strain, how do we calculate? Simple formula is half into del ui by del xj plus del uj by del xi. This is the analytical formulation, and we process that in the matrix form, which becomes a little difficult, which is what we were doing here, right? So in order to do that, you have to do the partial derivative of the shape function, and partial derivative of shape function looks like that, and the story doesn't end here, right? The story will again have a problem because you will have to convert this to local coordinate system. Okay, but I'm not going there right now. But this is how you do the partial derivation This is how you do the partial derivation and you calculate strain, right? Is this part clear? Just hold on. Will you? ये क्या है?
सर ये इजहाज के अप्रूवल है सर.
अच्छा अच्छा. लाइब्रेरी खुली रहती है क्या अभी?
सर अभी स्टूडेंट तो नहीं है ना, लाइब्रेरी खुली है.
खुली है. अच्छा ठीक है.
थैंक यू सर.
Okay, thank you. Okay, so sorry for that interruption. So displacement is from displacement we calculate strain, and from strain we calculate stress. Right? Is this clear so far?
Yes.
Is this making
Yes,
sense
sir.
so far?
Yes, sir.
Okay, so stick to the elastic problems only, and so from strain you can calculate stress. Once you have stress and strain value, you can also calculate the energy, right, which is this. So because I'm writing in matrix form, so I have to write transpose and strain, right? This you know, no? So this is strain energy density.
Yes, sir.
Okay, because this is the energy which is per unit volume, and this is because of the deformation in the material, right? If you have translation and rotation, you are not going to consume any energy. I mean, of course you are going to do some work, Newtonian work, but not energy, right? So the energy which is being stored or consumed or whatever is going to be only because of the deformation, which is strain energy, and because it is per unit volume, so you call it strain energy density. Why density? Because it is per unit volume, that's it. Okay, and now you have energy term, so you make it minimum. Okay, so once the energy will be minimum, then you can say that this is the stage of deformation which is stable, because this is the lowest energy state. Is this making sense? Is it clear? Is it as good as thermodynamics problem?
Yes, sir.
You calculate the energy of the system, but you will not only have strain energy, you will have a lot of energies. Sometimes you will have thermal energy, sometimes you will have some other energy form, and all those energy in totality will have to be minimized. And how will you minimize that? By taking the derivation and putting it equal to 0, right? So that is called the minimum energy criteria, or minimum potential energy criteria. Okay, so this is how finite element method really solves the problem. If we go in further detail, there are a lot of things to cover. Okay, as I said, here we at some point of time we will have to convert from local to global, global to local back, okay, back and forth, and here we will have to deal with a lot of things like elasticity, which is isotropic. If not, then anisotropic, or plasticity, creep, viscoelasticity, and damage. All those things will be incorporated here in the material's stiffness. Okay, so there we will have to do a lot of things, and then in order to calculate the energy in one element, you have to do the integration of this. Okay, and this integration will be done. So because it is per unit volume, no, so you will have to find out what happens in the total volume, how much total energy is there, and in order to find out that, you will have to have right? So you'll have to do this integration from -1 to +1, -1 to +1, and this is in local coordinate, right? So you remember this is zeta, this is eta, it always goes from -1 to +1, -1 to +1, right? And this is per unit volume, and thickness you always assume it to be unity. If so, I told you in abacus you can give a value to this, so that will be thickness of the element, so that will be simply a multiplier here, okay? So you will have to do this integration, and that integration itself is another problem which also we will learn in great deal, okay? But in nutshell, this is what the software is doing. So step number 1, step number 2, step number 3, step number 4, and after step number 4 you have the final value of everything in one element, right? And you do the same thing for all the elements and put them all together, and then you have a final solution. So is it making sense to you that how these things are being calculated?
Sir,
Yeah.
while finding the minimum potential energy,
Hmm.
what are we changing exactly? By if we found out a minimum particular potential energy, so then we calculate the U with respect to that, the
No.
displacement.
Yeah. So you have some unknown variables, right? So you have at certain nodes you do not have the value of the displacement, and at certain nodes you do not have the value of the force, okay? So you have some unknowns in these equation which is coming until here, and how do you solve it? You need an equation, right? You need a criteria to solve it. So far
Yes.
these are just parameters. Strain is equal to that, stress is equal to that, energy is equal to that. But then what criteria you put so that you have an equation to solve? That criteria is that the potential energy has to be minimum. That means the derivative of this has to be less than 0. Equal to 0. Yeah.
Yes, sir.
Okay, so once you do that, then you have an equation which you solve, and you can solve it iteratively, right? And then, so for example, you have an unknown value of displacement at certain node, and let us say that more than one values are giving you but more than one value cannot give you that deformation. So you will always have to fulfill this criteria, that the potential energy minimum, and in solving that you will get the value of displacement, that this should be the displacement for the minimum value of potential energy. Okay.
Yes, sir.
Okay, so this is what happens inside the software, and so the whole algorithm it demands further details of each and every step how we do it, okay, but that we are not going right now. Now let me come back to what we are doing in the modeling part. So in lab 1 I think lab 1 was cantilever. So in lab 2 we have taken an axis symmetric problem. So because Yatin was saying that the screen was not visible and he was also not here, so I am repeating it, but I am not going to do this again and again. So we took this, which is a tensile sample, and usually the tensile sample is this, okay. So now I cannot undo it. Okay, so this is the whole tensile sample, and we are not interested in modeling these areas, okay. We are only interested in modeling the gauge length, which is the parallel length specimen part, okay. So that is what we are modeling, the gauge length part, which is a cylinder, and that cylinder is axis symmetric. So we only take one axis symmetric film out, and then we model that, and now we will come back to the other screen. I am stopping here unless somebody has something to ask. Okay, so let me stop it here and let me share it there. Okay, so do you see the other screen?
Yes, sir.
Okay,
Yes, sir.
so what did it save? Okay, sp2.save. Okay, fine. So this is the object which we made, and I will make it today again for the sake of revisiting how we did and what we did, and then we will finish this. And for today's work there will be no lab report, so you don't have to submit any lab report next week. Okay, but I hope you understand this well and use this time not to do anything else but understand this. If so, Avnish, has Dishant joined?
Yes, sir.
Okay.
Yes, sir.
Yeah, Dishant and Rohit and Avnish. So Dishant and Rohit, you be here after I finish, and whenever you get time, you engage with these students and try to find out what they are not understanding. Okay, and I think Santosh can also do some work on Abacus, and once you catch up, Santosh, once you are able to model this, maybe you all three can help the students to solve their problem. And there are some analytical problems which I gave in the first part, which they were doing. So if they have any issues, you can try to solve that also. It's just a few calculation. Okay, it's not related to software or finite element analysis. Okay, just some calculations. Once Santosh catches up with the Abacus, and Avnish knows a little bit of Abacus, Rohit also knows. So you try to solve the problem of students if they have any, and try to engage with them and understand where they are facing the problem. Okay, once you gauge that, you also let me know. You try to solve it at your own end. If you cannot, then you also let me know what is the real problem. Okay, and make them practice as much as possible. Okay, is this clear?
Yes, sir.
Okay, so I will do it again today, what we did previously, and the plastic part and how we generate the data for yielding, that I will not do. That we have done. You can see the lecture of the previous semester or the previous lecture, and you can get it from there. So let me open this again, and a little bit about the software I will tell you. So this, of course, you have to install. Okay, and I'll have to change the resolution, which is an issue always. So 17, this is very small. So let us try 1920,080. Okay, so this is the software which you install, and then you have a lot of modules here through which we will go one by one, and we will make the model again. Before that, the first thing and I am telling you something new today, so those who are here, please be ready to absorb this, and those who are not here, I really feel sorry about that. Okay, what else? Avnish, can you take second round of attendance again, quick?
Yes, sir. Adarsh.
Yes, sir.
Ankit.
Yes, sir.
Asima.
Yes, sir.
Bobby.
Present, sir.
Charwak.
Yes, sir.
Gokul.
Yes, sir.
Arjot.
Yes, sir.
Aswani.
Yes, sir.
Kanupriya. Shivaji.
Yes, sir.
Prem.
Yes, sir.
Praveen. Rishabh.
Yes, sir.
Satyaprakash.
Present, sir.
Shyam Sundar.
Yes, sir.
Vedant.
Yes, sir.
Yatin.
Present, sir.
Sachit Anand. Sachit Anand.
तुमने उसको 2 बार बोल दिया, पहला क्लास है वो चला गया। कोई बात नहीं। ओके, सो द इम्पॉर्टेंट पार्ट is one, and then I will tell you another thing which has a good implication. Okay, so first thing what you have to do is you have to set your work directory, which means that you have to make a drive where all the calculation files will be kept so that you can track it back. This I have showed you once and I'll show you again. So you go to set work directory and this will not open. Okay, so there is a problem always. So this is happening because of resolution. Okay, so here it is, you set so you see this small window and there you can set your work directory. So I have made this work directory, I'll make another one. So analysis. So you can give any name as per your wish and click that and make it your work directory. Click OK, and then let me go back to, but I'll have to come back to this anyway. So before doing that, I'll do one more thing, which is so once I have made the work directory, you go to file and you click on macro manager. Okay, and this small window opens up which asks you to create a macro. So you start creating a macro and you have two options. The directory is home directory or work directory. You click on work directory and then continue, and then you see a small window which tells you recording macro 1, and there is a button of stop recording. So once you click on that, the recording will stop. I'll tell you at the end what it records. Okay, so now this we have done, and now I will change the resolution. So 1920,080. Okay, so this is the macro which is being recorded. Okay, now we are in the parts, and I'll without much explanation, I'll just do what we did before. So as I said, it is an axis-symmetric problem, the tensile sample. So I choose axis-symmetric. You obviously have two other options of 2 dimension and 3 dimension. And this is going to be a deformable body. That's why you will get strain in the body. If you choose rigid body, you know that rigid body cannot take strain. It can only translate or it can rotate. There will be no deformation. So we are not choosing rigid body, so we choose deformable. And shell is okay. This is not that the element will be a shell, this is just a feature, don't worry about it. And we continue and we come to a sketch part which is similar to AutoCAD or other drawing software. So here this line, so all the grid lines are in blue color. There is one line which is not in blue, it looks green to me. And there is this datum point which is the center of your axis symmetric space. Okay, and this is the line which is the axis along which everything is going to be symmetric. Okay, I hope axis symmetry is clear to you. What is axis symmetry and what I mean when you have an axis along which the things are symmetrical. Okay, so if you have a semicircle, that is an axis symmetric part of a sphere, and the axis is the center of that sphere, right? So we have to make a cylinder, and for that we have to make just a square, I mean a rectangle, which is going to be like this. Okay, and on axis I don't think there is a line needed as far as I remember, but I might be wrong. We have to give some dimension. So this is the radius of the cylinder, and this radius of the cylinder, let us say, is 5 millimeter. So this has shifted there. Okay, so let me do it without removing that part. So now if I change the dimension to 4, okay, not 4, 5, no, so make it 5. Okay, so this is 5 millimeter, and the total length is usually, for according to the ASTM standard E8, usually it is 4 to 5 times of the diameter, right? So this is 5 millimeter. This is too huge, I think. Usually is the size of the diameter, so the radius will be 2.5, and the gauge length we can make of 20 or 25 millimeter. So I'll make it 25. So this is my tensile specimen axis symmetric part, and then I say done, and this is the object which we are going to model. Is there any confusion so far here?
No, sir.
No, sir.
Okay, so we have made the object, and now we have to tell that what is the material by which this thing is made up of. So first we will create that material. So we go to from the part module, we go to property module, which is just next to the part module, and you can see all these modules here. Also on the left hand side there is a tree. You see more information than the modules which are listed in this pop-up menu. Okay, so we go to property and we click on create, and here comes the window where you can define your material. I can give it a name. So you can model whatever material you are interested in. You can put nickel, super alloy, Inconel, and steel and aluminum and FRPC and what not, all kind of materials. So for simplicity we will take steel, and you can write in description. This is not necessary or mandatory for the modeling. This is for your own reference, right? If you are working on n number of materials and you think that you can forget what was the material, you should be writing the description by clicking on this pencil button, but we are not going to do that. And then you have different types of properties which you can use to define your material. The question you have to ask yourself is, what is the result you are looking for? If you are looking for the stress and strain kind of result, so if it is a stress analysis kind of modeling, and you are interested in those kind of deformation which are not time dependent usually, then you should simply go to mechanical, and you have to define elastic, plastic and those kind of properties, right? And so we go to mechanical, we go to elasticity, and you choose elastic, and in elastic then again you have a lot of options which you can utilize. So for example, the materials can be isotropic, the material can be orthotropic and isotropic. Traction is something which we will use in damage once, maybe we will use it, and coupled traction and shear and lamina is something which you use in composite. If you remember, we read a little bit about the composites in MM302 course. We will also read about the composites in the polymer course in the second part, and there maybe we will discuss what a lamina is. And then if you have to define a complicated material where you can have elasticity modulus different in different directions and a complicated material, so then you go to engineering constants, where you can define all the component of the elasticity tensor. Okay, so you see E1, E2, E3, and this is mu1, mu12, mu13. So Poisson's ratio in 1 direction, 1 2 direction, 1 3 direction, 2 3 direction, shear modulus in 1 2, 1 3 and 2 3 direction. Okay, so all those elastic variation, elastic modulus variation you can use in if you choose this form. So we will choose isotropic because the steel is isotropic material often, and usual elastic modulus of this steel at room temperature is 200 gigapascals. One more important thing I am again telling you is that the Abacus software which we are using has no units. So you have to be unit consistent always. So if I define the dimensions in millimeters and then my modulus and stress and everything are usually in megapascals. Okay, so because the value of elastic modulus of steel is 200 gigapascals, if I convert that to megapascal, that will be 200,000. The value of Poisson's ratio for steel is usually 0.3 to 0.33. So I will take 0.3, you can take 0.33, it does not matter. Then there are a lot of options which you can play around. You can open it and see what is there, fail stress, fail strain and all those things. And if you are really interested in something, a simple way of doing that is to go to Abacus manual and read about that. You do not have to read the whole manual. It is just for those who are extra interested in this. Okay. So for now we stick to isotropic, and we have given elastic modulus and Poisson's ratio, and from this we can do all the elastic calculation. So we have done plasticity. This is just a recapitulation of what we did. So I click OK, material has been made, and then I have to make a section. Section making simply means that what kind of element or continuum space you are in. So my material is homogeneous, it is not a composite. Okay, generalized plane strain we will not talk about, and it is a solid. So here is the window where we tell the model that we are dealing with solid elements and not shell elements. Okay, so shell elements will, if you remember, shell elements will need rotational degree of freedoms also. Solids will not. So we are choosing solid because our material is a solid material and it does not fall in the category of shells. And so the section is made homogeneous solid. I continue with that, and this is the option where it asks for that what is the thickness of your sheet, which is in plane strain and plane stress condition. Okay, it does not matter if it is plane stress or plane strain, really plane stress or plane strain, it does not matter. It simply is asking, if the problem is two dimensional, what is the thickness dimension? This is what it is asking for. If you remember the first part of today's lecture, I told you in the integration part where the minimum and potential energy criteria is, there is a parameter Te, which is thickness of the element, and that thickness will be multiplied whatever value you give in here, but that will work for two dimensional problem. It is an axis symmetric problem and there is no thickness here. Okay, so you just click OK and the section making is done. Now you go to the third one from the top, click there, section assignment manager, create, you select the object, you see the message here, select the regions to be assigned a section. You select this object, click done, and then it asks which section you want to assign because you have made only one. So in the pop-up menu you will see only one. So it is already selected, it is solid, homogeneous, the material is steel, and then we click OK. It should have become green. I don't know why it is not green so far. Yeah, now it is green. So some graphics issue. So material has been assigned to this. Now we go to assembly. Assembly, I told you what it is. So if you are making an engine, or if you are modeling a railway track or a railway wheel, then in order to do that you have to make railway wheel, then you have to make shaft, then you have to make the rail, and then in the assembly you have to put all those things together, place them correctly and join them, right? So that is what assembly means, assembling different items. We only have one item, so we don't really need to assemble many things, but even then we will have to bring that object to this space of assembly. By clicking on this one, you do that. And then there are two options, dependent or independent mesh, and that really means simply this, that if you make it dependent you will have to mesh it in the part module, if you make it independent you will have to mesh it in the assembly module. That's the only difference. So I will choose independent, you can choose dependent, it really doesn't matter. And we really don't have to do anything in this assembly except bringing the object in. And now we go to step module. Step module is the place where I tell the model that we are going to deform this material by certain amount, and we are going to deform it using static, so very slow deformation. So there is no time dependency, and we are going to tell that the time period from the beginning of this deformation to the end of deformation is going to be 1. This is a pseudo time, this is not a real time, this is a computational time. You can put it 0 to 10, 0 to 100, whatever value, but again you can normalize it to 0 to 1, so it's better to give it 0 to 1, and then you have to tell that what should be the increment size. So let us say that you have to deform the material by 2 millimeter. So how much smaller calculation you want to do, so how much displacement you want to apply stepwise. Okay, so if I say that divide the whole deformation into 10 divisions, then 2 divided by 10 will be 0.2. So 0.2 millimeter will be the deformation which will be given for one calculation, and then the software will calculate all the values, stress, strains, displacement, reaction forces, this, that, and it will create a file, and then it will calculate the next 0.2 millimeter deformation. It will do the same, writing down everything, and then again and again, so far and so forth. Then you have to define a minimum value, so we go to step, and you have a lot of algorithms here. You can solve dynamic problem where you have a lot of high velocity things, you have thermal problems, you have electrical problems, okay, you have heat transfer, mass diffusion, and all those things. So we will choose a static general. Static meaning the deformation is not time dependent. We continue with that, and the time period is 1. You can give any value, it doesn't matter, it's a pseudo time. NL geom means non-linear geometry. We will discuss this later on. So for now it is off, and here we define how many number of increments. I'll put 1000, I will tell you why, and I'll put 0.1 and maximum 0.2 and this 10 power minus 9. The meaning of this is the increment size. Initial value is 0.1, that means it will start with an increment of 0.1, okay, and then 0.1 of time, and then it will try to maximize this to the maximum value of 0.2. Okay, the increment of each division is 0.1 value of the total time. So total time is 1, so it is going to be 0.1. It will start from there. It will try to maximize to 0.2, but if the solution do not converge, if the equations are not being able to solve because of some problem, then it will try a smaller division, okay, and if there also solution doesn't converge, it will try further smaller division, and to what minimum value it can go for a division is defined here by the minimum value, and how many number of increments it can try for convergence is this, okay. So this is what we define, and we are done. Step is defined. Now we go to interaction. We really have to do nothing here, and then we go to load, and here we have to define our boundary conditions, which is the boundary condition is simply that here you apply, here I want to tell that this edge is not moving, and the upper edge I am going to pull it by 2 millimeters, okay. So I create first boundary condition, which is going to be a symmetric boundary condition along y axis, and then I choose this edge and I say done, and I choose y symmetry, that means symmetric along y axis. Okay, and then I say okay, and then I create another boundary condition where I have to apply displacement on the upper edge, and I have to apply displacement of now that box is not being shown, so I have to change the resolution again. So here it is, and if I change the resolution back, yeah, okay. So here I will say that the upper edge does not move in the x direction, that means horizontally, so that is 0. U2 I am going to apply 2 millimeters, and rotation I am not bothered about, so it can rotate, it cannot rotate, so I am not putting any value there, and I say okay. So then you see with this arrow the boundary conditions are being shown. Okay, so this is being pulled up and no movement in the horizontal direction, and this one is fixed on the lower side in the y symmetry. Okay, so those are the boundary conditions I have given. Now I go to mesh, and here I have to define by fourth tab from the top on the left hand side. You have to tell the model that what kind of element you want to choose. Okay, so we want to choose a linear shape function, so geometric order is linear. We are going to use an implicit algorithm, so we will choose a standard and not explicit algorithm. The type of element is going to be axis symmetric stress calculation. Reduced integration, I will tell you what reduced integration is when we will deal with numerical integration in the theory class. For now, it is a integration algorithm. I told you in the first part that you have to integrate the stress transpose dot strain into d zeta d eta, right? So that integration is going to be not analytical integration but numerical integration, and you can reduce some parameters there, and that is why it is called reduced integration, and everything else is done. So finally you see that this is the type of element which will be solved. So the total description of that element is here. So this is a 4-noded bilinear axis symmetric quadrilateral. So it's a rectangular which has a 4-node, okay, and it has reduced integration, hourless control and everything you forget about, and say okay. And now you choose the second button from the right hand side top, and you tell that I only want quadratic elements. I don't want trigonal elements mixed with quadratic elements, that I do not want, and I want everywhere regular meshing. And then you say okay, and then you have to tell that what should be the size of the element. So I will give 0.2 millimeters and I apply, and then I click on this one, say yes, and it is meshed. Okay, so you see the elements have been formed. Okay, now meshing is done. I go to job, and then I create, and I call it elastic axis symmetric steel sample with 0.2 millimeter of element size and 2 millimeter of displacement applied. That is the name I have given. I say okay, and then I submit the job. Okay, and the job is submitted, and then I go to monitor, and here you will see the messages that the analysis of input file has started, the analysis of input file has completed, then the calculation has started, and you see the calculation happening here, and then the calculation has finished. So the analysis has been done, and now you click on results, and you see that the sample has been extended by certain amount. If I play the video, you can see how the extension is happening. Okay, and the stresses are not changing locally drastically because it is a elastic problem. So there is no plasticity, there is no damage, nothing. So it is just gonna extend like rubber. So it is going to be shorten in the radial direction and going to be longer in the gauge length direction. Okay, so this is what was expected and this is what is happening, and this is how we model it. Okay, so I have just revisited what we did, and now I stop recording. Okay, and this recording has stopped, and you see that there is a message which says macro 1 has been added to the work directory where you made this. Okay, so now I go to my work directory, which was where? Which was here somewhere. So where is MM302? Here, and we made reanalysis is the work directory, and here you see that I must have a Python file, abacus macros, and this I can open it in the Python shell or Notepad++, and you see that a code has been written, okay, in Python language, and this is the file which was made by recording the macro, and that is macro 1. Okay, and I'll just do this last thing and then I will end this session. Is the following: you read these lines, it says that coding blah blah blah, do not delete the following import lines. So what I'm going to do is I'm just going to copy this, and I'm going to create a new one and paste it here. Then I go back to my macros, and instead of this def macro and brackets and colon, I'm going to take all those lines and I'm going to copy that and I'm going to paste it just after this, and I'm going to save it like a Python so that I get those colors in this. So save as, and reanalysis, I'll just put it tensile python.py, and now I have all those coding colors here, and I have to dedent this because that has an extra indent. So I am just going to decrease the line indent, and now it is okay. And now any one of you are wondering what this code is, or do you have any idea what this is? Are you guys there?
Yes, sir, but I don't know, sir.
You don't know?
But I think what we have modeled,
Yeah.
that got stored as a code, and this is that code, I think.
Yeah, you are correct. Was it Harshvardhan?
Yes, sir.
Yeah, so you are absolutely right, and this is like an extra bonus to us that you don't have to write any code to model this. Abacus has written it for you. Okay, and if let us say that the tensile specimen which I made was having a radius of 2.5 millimeter, if you remember, and gauge length of, oh, I forgot to do something which now I cannot change. Okay, fine. So okay, so well, we cannot do what we wanted to do because there is you have to tell Abacus before the recording starts so that it records everything based on coordinates, and because we did not do it, Abacus usually masks all the coordinate values and the selection of edges and points and things like that. So for example, when you apply boundary condition on the upper edge, that upper edge can be selected by coordinates, but that will not be recorded because we didn't use that. We didn't tell Abacus to do that in the beginning. Okay, but let me see if it is there. So you see, basically what is this? This is the first, what we did was we created a geometry. Okay, so this is what it is. it creates a sheet size where you could sketch everything, and then it just defines that the sketch points, and we had a construction line which is the axis of the axisymmetric space. Okay, and then we drew O, so that means we somehow have told Abacus to put it in terms of coordinates, looks like. So the rectangle which we made initially, if you remember, so here we made this rectangle in the sketch, no? So this rectangle was sketched by joining 2 points, and those 2 points are these. Okay, and then we assigned dimension to that, then we changed the dimension. Okay, and we changed the dimension first to 5, and then I said that the radius has to be 2.5, so that is here. So what I will do is I will make it I'll make it 1. Okay, and so I have changed it 1. So this can happen. So for instance, you have tested n number of elements and you want to model that, and the dimensions are a little bit different. So you don't really have to model the whole thing on the user interface. You can just change a few things here and there and run this code, and everything will be done for you. So for instance, I change the geometry. I make it 1 millimeter in the radius, and I make it 50 millimeter in the gauge length. So I make it like a wire. Okay, so here I change it to 50. And then all these lines are just the recording of the views and going from one module to another module. And then at certain point we must have defined the material, so that information will also be there. In the material we have given Young's modulus, which is here. So you see 200 megapascal and 0.3 is the Poisson's ratio. So here we are defining material, name steel. Okay, so I can change the name if I want to use aluminum alloy, and I can change the material properties. I can just write 110 gigapascals, and 0.3 is okay. So some masking has been done here. Okay, and that is it. And let us say that I want to apply different boundary condition. Instead of 2 millimeter, I want to stretch it by 5 millimeter. So that I can change here, where I define the boundary condition, and instead of 2 millimeter I will write 5 millimeter, and then I will save it, and then I will go to Abacus and I will create a new file, because you might not trust this magic of coding. So I have deleted the previous file which we made. I actually didn't save it, and now I'm going to run this script, which is tensilepython.py, and here we have changed the radius to 1, gauge length to 50, and we are stretching it by 5 millimeters. So I just double click on this, and there is an error, which is what I was expecting. The error is in line 62 module this because I changed the name of the material to aluminum, I didn't change the further coding. So it is here. I changed it to aluminum, and here it is steel, so I have to change that to, I actually have to change everywhere from steel to aluminum. So I will change all the steels to aluminum, replace all, and file, save, and then I will try my luck again. So no, and run script, and no error. Okay, there is an error because of something, but that was in the job module, so everything else is okay. So you see that instead of the previous model, this is thinner and longer, so the geometry has changed. If you want to really confirm it, you can go here and edit on sketch, and you can see this is really 1 millimeter. You see it is 1, and this is 50. So that has changed according to our code. And if you go to boundary conditions, and you see that it must have been asked to stretch by 5 millimeters, which is correct. Okay. So all those changes you can do in the code, and that is the importance. More importance is, I mean, you can do a lot with the code. You can do a lot with the code. If you just want to use elastic plastic, so I don't really have to model all those things. I will just add here after this material elastic table. I can add a few lines for the plasticity, and it will be done. Okay. Further advantage of coding is that you can use a lot of Python specialities, like you can use for loop, you can use for loop for putting boundary condition, let's say on each node differently. So that also we can do. Okay. So that's the advantage of this, and with this we end this session. This was a revisit session. I hope it has helped you, and there is no need to write any lab report for the next week. Practice this and the previous works, and sit with the TAs and discuss with them, and if you have any difficulty, come to me first, and then we will see. If we cannot solve it, then of course you can do whatever you want to do. Okay, is that okay?
Yes, sir.
Okay, all right. So we end this session. I mean, I'm going out, so you can still sit with the TAs and discuss your problems.
Sir,
Yeah.
Sir, what about data?
Which data?
Sir, data you were supposed to send us for that elastic plastic lab report.
Yeah, but you have to remind me what was the data.
sir, it was an Excel file, right? You basically reduced it to 74 values, I guess.
Oh, that data.
Yes, sir.
Load displacement value.
Yes,
Was
sir.
it load displacement value? Yeah. From that you have to find out the
Flow
stress and strain,
stress
no?
and plastic strain, yes, sir.
Okay, okay. So let me see where it is. Elastic plastic. This looks like it. Elastic plastic is already open. When did I open it? Anyways, do you want to reopen? No. Okay, so you want load and displacement, from which, so force and displacement I'll give you, because that is already small data, no? ये तो आधी ही ड्यू है. हाँ, इसको मंडे तक हो जाएगा. 31st कर देता हूँ.
Yes, sir. Yes, sir.
Yes.
Yes.
Make it 31st. Okay, data is there now. ठीक है. और कुछ मिसिंग था?
Okay, sir. Thank you, sir. No, sir.
Okay, all right. So then I'm leaving. If you want to discuss, you discuss with the TAs. Okay.
Yes.
Okay.
Thank you.
Hmm.